All right, so good morning slash afternoon, I guess. So we're supposed to be going over chapter 11 stuff, but since you guys are the first ones here, if there's a topic that you kind of want to talk about, then go ahead and put it in chat, and we'll start with those, and then we'll go from there.
I thought we were doing chapters 8, 9, 10, 11, 12, I think.
So it's 9, 10, 11 for exam number 3. And so we did 9 and 10 yesterday. And so we'll start off with chapter 11 first. And then if no one's got questions on chapter 11, then we can go back.
What's the typical chapter 9 question and chapter 10 and chapter 11?
So chapter 9 is like your Lewis structures, right? Chapter 10 is a lot on your molecular geometries.
Like the Vesper theory?
Like the Vesper theory.
Because I'm looking at the examples that you have right now, and those don't seem like... I think whenever I see it in a question like this, like a test question, I like blink out and I don't really know because it's not in a question that I'm used to.
Yeah, right. So the ones that are on the screen, these are much more about like intermolecular forces, right?
Mm-hmm.
And so this is more chapter 11 type of stuff. So is there anything in particular that you two want to go over for chapter 11? Otherwise, we can just start with some of these and we can see how they kind of play out.
Let me look at a video from the chapter 11 that you posted, but just like really quick so I know what.
Was there anything you wanted to see, Anthony? All right, so let's just go ahead and let's jump into these. All right, so we kind of have, let's look at this 2004 one, and we're going to look at these first 4 up here. And so we're trying to explain these observations that we see, right? And so on the first one, it's asking us why is fluorine a gas compared to that of our no, what did I do here? Why is fluorine a gas compared to our iodine being a solid, right? And so we're trying to figure out that difference there, right? So what force determines whether you're a gas or a solid? What dictates that? Are you guys here?
Yes, sorry. I just barely found my homework that I've been looking for math. And
so,
I did a while ago.
That's all right. So let's look at this one, right? So we're trying to compare between our fluorine and the iodine, right? So we're trying to figure out why one of these would be a gas and why one of them is a solid, right? So anytime that we talk about phases, right? Deciding if something's going to be a solid, a liquid, and a gas, what determines that? What's determining whether something should be a solid, a liquid, or a gas? I'm sorry, what was that?
Isn't it the boiling point? Right?
So boiling point is part of that. And so what kind of force determines the boiling point for a material?
Electronegativity? No.
So it's not necessarily electronegativity, but what have we learned that should be tying us together with solids, liquids, and gases?
Enthalpy changes.
It's so inter or intra, right? So is it INTER or INTRA? Which one of those has to deal with our phase changes?
Intra, because it's internal. Inter.
Isn't that a trick question?
It is
But-
not a trick question.
I think you're referring to inter, but if it's intra, that's a lot of energy.
Right? So intramolecular forces has to deal with your covalent bonding, your ionic bonding. Those are the things inside of the molecule that hold the molecule together, right? Inter is the ones that are the forces between the molecules. So those are things like London forces, dipole-dipole interactions, hydrogen bonding, right? So those are intermolecular forces. Intramolecular forces are things like a covalent bond, an ionic bond, a metallic bond, right? So those are the things actually holding the molecule together, right? So normally whenever we're talking about solids, liquids, and gases, you want to be thinking about IMFs. So you want to be thinking about your intermolecular forces. So in order to do your intermolecular forces, what are we going to need to know about F2 and I2?
Their states.
We know their states, right? But in order to determine what kind of intermolecular forces that they have,
Their Lewis structure.
we're going to need their Lewis structure, right? We have to look and see how they are connected. Because if we don't know how they're connected, we can't answer all of the follow-up questions. So we need to do the Lewis structures for both of them, right? So we have F2 and I2. Yeah. And so once we have this, then we should go ahead and we should classify that bond. So the bond between them, would you consider that to be an ionic bond, a covalent bond? What do you guys think? So the F to F bond or the I to I bond? What kind of bond is it?
Ionic.
Isn't that covalent? Because ionic doesn't it have to have ions?
So ionic doesn't mean that it has to have ions. Ionic means
I mean-
that they should be ions, right?
Cation and anion. But
Yes, so it's a cation and an anion. So how can you tell if you would have a cation and an anion?
you see if they're metals or non-metals.
That's the
Right? So metals and non-metals is one way to do it, but we should have a better way to do it now.
Cations are positive, anions are negative.
Anions are negative, cations are positive, right? But you should be able to find them by their electronegativity difference, right? So if you have a big electronegativity difference, then you would know that it's ionic, right? And so that cutoff value is about 1.7 or 2.0, right? So different places will use different ones, but basically in that range, you're looking at an ionic bond, right? Now, for fluorine and fluorine, is there a big electronegativity difference between one fluorine atom and another fluorine atom?
No,
No.
No. So is it going to be an ionic bond?
no.
No, right? So what kind of bond is it going to be?
Covalent.
So it's a covalent bond. And is that going to be polar or non-polar?
Polar. Non-polar.
Why would it be polar? Why would it be non-polar?
I get confused with the polars and the non-polars, isn't it? When there's like a big major difference in electronegativities,
And so if there is a difference in
then it would be
electronegativity,
polar.
it would be polar,
it's
right? So if there's a difference, then it's going to be polar because you would have a positive side and you would have a negative side. So you would be basically making two poles. So you know how on the Earth there's a North Pole and a South Pole?
Yes.
One side is magnetic north, so it's a positive side, and one side is magnetic south, which is the negative side. So that's kind of how they get their names about their poles. Now, actually, I don't know if north is positive or negative. That part now, I might have those flipped. But either way, there's a positive side of the Earth, there's a negative side on the Earth, right? And so this is the same
Do you have a way of remembering the bonds, like a saying or a phrase to memorize the bonds?
So I don't have a phrase to memorize the bonds, right? I just know that covalent bonds means that they're sharing those electrons. Ionic bonds mean that they transfer it, right? So if they are close in the electronegativities, then they're going to share it and they're going to make a covalent bond. If they're different by a lot, then they can transfer it, and that's going to be an ionic bond. Now, between our covalent bond, we have a non-polar covalent and we have a polar covalent. So a polar covalent is kind of in that medium range where you get some electronegativity difference, but it's not enough for it to be ionic, right? So that just means that you only get partial custody of that electron. Whereas a non-polar bond, it means that they're really close with their electronegativities, and it's going to be evenly split between them. And so that's what's going to be a non-polar. And so in this case, this is going to be non-polar for both of these because there's no electronegativity difference inside that bond. So that's our beginning part, right? So both of them have a non-polar covalent bond. So what Vesper geometry is F2? How does that molecule look? Linear, right? And so both of these are linear. So if I was to ask you if that molecule was polar or non-polar, how would you guys classify it?
Polar, that's if it's dipole, right? If it has
So
a
yes,
charge
polar
on
means that it has a dipole moment.
So let me see, these two are not because they are, well, they don't have significant difference in the charge.
All right.
Uh,
So
put it that way.
they only have one bond and there is no difference in their bond, right? There's no polarity to that covalent bond connecting one fluorine to another. And so you're right. This should be nonpolar. And this one is nonpolar. Okay. So now that we know that this is a nonpolar molecule, we should be able to talk about what kind of intermolecular forces there's going to be. So what are our 4 options for our intermolecular forces? What are the 4 options for our intermolecular forces? So if you remember one of them, you can say that, and we'll try to build up our 4. We have dipole-dipole. Very good.
Dipole moment?
So dipole moment is still dipole-dipole. We have London dispersion forces, but I like to call them just London forces because sometimes I think it's confusing that dispersion forces are actually holding things together. But we have hydrogen bonding. And then you're right that we would have an ion mixed with a dipole. Okay. So out of those 4 options, which one is the weakest? In general, for most molecules, which of these forces is the weakest? Very good. Our London forces is generally our weakest force. What's the next one up from there? After London forces, who would be the second weakest?
Ion dipole.
So ion dipole is not very weak at all, right? Because your ion has a charge and your dipole has a partial charge. And so that's a pretty strong attraction there, right? Dipole-dipole is weaker than that because each dipole is only a partial charge. So now you have 2 partial charges coming together. And so that's a weaker interaction compared to an ion dipole where that ion has a full charge that's interacting with the dipole or partial charge on the other one. And then where does hydrogen bonds fit in compared to an ion dipole?
They're not as strong as ion dipole, but they're the strongest otherwise.
Very good. So hydrogen bonds are kind of like our strongest of our other intermolecular forces, right? So not quite as good as an ion dipole, but better than most dipole-dipoles, right? And so this classification, there are times where they can be mixed up. So there's like a gray area where they can be overlapped. But in general, this is the pattern that they fall, or that they follow. It's going to be London forces as your weakest, then your dipole-dipoles, your hydrogen bonds, and then your ion dipoles. Right? And so that's generally how they fall in. So when we look at our F2 and our I2, what forces do they have inside? Actually, here, let me make this a little bit bigger. What forces do they have for our F2 and our I2? What intermolecular force holds them together?
Well, for sure, dipole, right?
Why would there be a dipole-dipole?
Oh, wait. There's no dipoles on this one. It's only London dispersion. Van der Waals.
So we would only have London forces. So all molecules have London forces because London forces happen if you have electrons, and pretty much all molecules have electrons. So that's generally it. If you can come up with a molecule that has absolutely no electrons, then you could not have London forces. But if you have electrons, you're going to have London forces. Dipole-dipole only occurs if you're polar. Right? If you don't have a dipole moment inside your molecule, you can't have dipole-dipole. What do you need to have hydrogen bonding? What kind of forces?
Hydrogen.
You definitely need a hydrogen, but what does your hydrogen need to be connected to?
Typically with fluorine, oxygen, is it nitrogen?
Fluorine, oxygen, and nitrogen. The fun group, right? But really, it's the top three on your periodic table, right? So they're sometimes called what the electronegativity hogs, but basically they're very small and they have very high electronegativities. And so what's going to happen is they're going to pull that electron far away from that hydrogen. And so you need that hydrogen, and it has to be connected to the fluorine, the oxygen, or the nitrogen, right? So just having the nitrogen there and then having something like like a carbon and a hydrogen, this doesn't have a hydrogen bond because that hydrogen is not connected to the nitrogen. But that one has a hydrogen bond because the hydrogen is connected to the nitrogen.
By the way, this is the easy way I always remembered it. Water, because the H2O, the hydrogen and the oxygen. So
yes, but that's only going to get you one example, right?
Yeah.
So you're only going to know about the hydrogen and the oxygen, but there's two other elements that you also need to be aware of, right? So you also want to make sure that you know about the nitrogen and the fluorine. But yes, water is a good example of having hydrogen bonds.
Remember it as FON, or
I like it, or you can do NOF, right? Because it's nitrogen, oxygen, fluorine. So either one. But the first part about it is if you don't have hydrogen, you don't have a hydrogen bond. That's kind of the first step. But if you do have a hydrogen, then you need to see if they're connected to one of those three. Right? And then ion dipoles, this means that you have an ion and you have a polar molecule. Okay. So now we know that we only have London forces for our F2 and our I2. And so London forces get stronger with what?
dipoles.
So London forces are not related to dipoles. So we are not worried about dipoles when we talk about London forces. So what makes London forces stronger?
Bonding pair.
Right? So it's tied in with our molar mass. And why is that? Why are London forces tied in with our molar mass?
Gives them more electrons.
More electrons, right? So there's kind of two things that are happening, right? So remember that London forces happen because our electrons are moving around, right? So they can move all over the place. As those electrons move around, then what it does is on this other side, it causes kind of a ripple effect. So if more electrons are over here on the right, that's going to give this side over here a little partial negative charge. And so that's going to cause this side to kind of push the electrons over, and it's going to become partially positive in response, right? So that's why our London forces kind of are temporary and is based on the electron movement. Now, if you only have one electron, you could only ever get one electron over here on the right. If you have 100 electrons, then you can get a lot more charge to temporarily shift, on one side compared to the other, right? So the more electrons you have, the bigger these swings could be. Because now, however unlikely it is, if you had 100 electrons, all 100 electrons could possibly be for a moment on one side of the atom, right? So you can imagine that there's much bigger swings that can occur because you guys have more electrons. The other part is by being larger, it's more easy to polarize your electron clouds. And so it just makes it like, gives them more space to swing around, which makes them more easy to polarize. So you can get a positive side and you can get a negative side easier with larger sizes as well. And so molar mass, when that increases, so does our London forces. So looking at our two molecules, I2 and F2, who has a higher molar mass?
Iodine.
So let's be confident. Who has a higher molar mass, iodine or fluorine?
Iodine.
Iodine, right? So our I2 has a higher molar mass than the fluorine gas. And so it has stronger London forces. And if you have stronger London forces, are you more likely to be a solid, a liquid, or a gas at the same temperature and at the same pressure?
Could you repeat it?
If you have stronger London forces, are you more likely to be a solid at the same temperature and the same pressure? Right? You're more likely to be the solid. So if you have stronger intermolecular forces, you will have a lower melting point. You will have, sorry, not lower. You will have a higher melting point. You will have a higher boiling point. All of those things will be going up because you have stronger intermolecular forces holding those molecules together. Right? So you got to keep increasing that temperature before you have enough energy to kind of vibrate those molecules apart to create that transition. So iodine is a solid at 25 degrees Celsius and 1 atm because it has stronger intermolecular forces, because it has stronger London forces, because it's a higher molar mass compared to fluorine. Do you guys have any questions about that part?
I know in the the lecture, it kind of mentioned that there was something special about ionic dipole forces, like compared to hydrogen bonding. I guess could you go over that kind of briefly, like?
So an ion dipole can't occur if you guys only have one type of material, right? So an ion and a dipole normally doesn't show up if you guys only have a molecule, right? Because something like NH3 or NaCl, they're either going to have a dipole or they're going to be completely ionic, right? So ion dipoles show up when we start to have mixtures of things in there, right? And so it's going to show up when we have solutions. So they're strong forces, but they show up when we have a mixture or a solution because you need one material that's going to be ionically bonded together, something that has ions, and then you need another material that has a dipole. And so that's why we normally don't see it when you only have one material. You see it when you have two materials.
Okay. Also, are we going to go over any like molecular orbital theory or like bond orders today?
So we can. That's something that we can talk about. That's not a problem.
Okay.
Okay. So let's look at B now. So sodium fluoride has a melting point of 993 degrees Celsius, whereas cesium chloride has a melting point of 645 degrees Celsius. So why is that? Why are their melting points different? NaCl is not a gas at room temperature.
Oh, whoops. I'm sorry. I flipped it. Solid.
There we go.
I think it still kind of addresses this question that you just asked, is why is sodium fluoride, yeah, is it melting point is 993 and the melting point is cesium chloride is 645.
Why? How does that address it?
Well, isn't it? Let me just take a look. Oh wait, these are two. No. This one is because I have to take a look at my periodical table. Hold on.
So what do you guys think? What's the strong force that we're concerned with for this one? What's holding these materials together?
This is for the CSCl.
Yep, for the part B. So we're looking at the sodium fluoride and the cesium chloride. What force is holding those together?
No, it's because
So when you look at these, right, what kind of bond connects sodium and fluorine together?
ionic.
Ionic, right?
Chloride.
And so when we're talking about the intermolecular forces that are there, if it's an ionic bond that connects them together, it's not going to be dipole-dipole, hydrogen bonds, London forces. What holds that solid together? And so this is something called your type of solid, right? And so would you consider this to be molecular solids, or would you consider these to be non-molecular solids? Are these like a molecule where sodium and a fluorine are united and they travel together as a set? Or is it really like you just have this big collection of sodiums and fluorines and they just have a 1-to-1 ratio? What do you guys think? They're crystalline, right? And so this is that concept that when you have an ionic bond, you really have something that's positive, and then you have something that's negative. And when they make solids, they're really just this collection of positive and negative things holding each other together. So they're not really a molecule. These are non-molecular, right? So they're this collection of them, and they just happen to have this 1-to-1 ratio. So 1 sodium and 1 fluorine. So what's holding these together is their ionic bond is holding those things together. So you do want to think about what type of solid you have, whether it's molecular, so if it's a molecule, or if it's non-molecular. Does anyone else have other examples of something that's non-molecular? So we have the crystalline solids, right? Or the ionic salts. What's another type of solid that's non-molecular? What do you guys think? So you should review this, right? This worksheet that I linked. So this is the second part of your chapter 11. You guys should be classifying each of these as where they fall in, right? So if they were solid, what's the forces that hold them together? Are they molecules? Are they metals? Are they ionic crystals? Are they covalent bonds, but they're in the network solid, right? We should be able to classify all of our different materials into where they fall in, okay? And so we have the ionic bonds, which hold together our ionic salts. We have metallic bonds, which hold together our metals. And then we have covalent bonds that hold together network solids. And so those are the examples of when you have these solids that aren't molecules. So there are non-molecular ones. Our molecules, those are held together by our usual forces. So those are going to be our London forces, our dipole-dipole forces, or our hydrogen bonds. Okay. So when we're looking at our sodium fluoride and our cesium chloride, they're held together by these ionic bonds. So who has a stronger ionic bond, sodium and fluorine or cesium and chlorine? What do you guys think? And so why do you think cesium has your higher or your stronger ionic bond?
Compared to NAF.
Yeah.
I have it written down. I just gotta. I'm gonna check real quick.
So when you guys have an ionic bond that's formed, right? There's an attraction that forms between them. Does anyone remember what we call that attraction be something between something that's positively charged and something that's negatively charged?
Dipole.
So dipole-dipole is an example.
Between polar molecules, yeah.
But it's only between polar molecules. So that whole concept, right? Whether you're talking about molecules or you're talking about electrons in the nucleus, right? Whenever we have a positive thing and a negative thing, there's an attractive force between them. Negative and negative, we get this repulsive force. So what's that force called? It's named after a guy. And there's an equation that goes with it.
That'd be Coulomb?
Coulomb, right? So this is talking about Coulomb's attraction or Coulomb's force, right? So Coulomb's force, let me make some space here. is related to the charge of the particle and the charge of the other particle and the distance that splits them up. So the radius squared, right? Now there's other factors in that and conversion things that to convert the charges into a force. But this is our basic example of Coulomb's force, right? So the larger the charges are, let's say that this is a +1 and a -1, then this becomes -1 over r squared. And so that force attracts them together because it's negative. Okay? If we were to increase that to a +2 and a -2, we would now be -4 over r squared. And so that's an even bigger force. So the bigger your charges are, the more attractive the force is or the more repulsive the force is, right? What's the second part besides the charge of our particles that matter?
The distance.
The distance between them, okay? So let's go back and let's look at our molecules, or not our molecules, but our solids that are being held together. What is the charge of sodium if it's an ion? +1, very good. And fluorine? -2 would be oxygen. What would the charge of fluorine be? -1, very good. And then let's look at cesium. What's the charge of cesium? +1. And chlorine? -1. And so if we're comparing those forces, both of them have the same charge, right? So both of them are going to look like this top one here. So we know the charge isn't going to determine the strength of their bond or the difference in it. So instead, what do we need to look at? If it's not going to be their charge, it has to be their distance. So now let's look at this part. Who is bigger, sodium or cesium? Whose volume is larger, a sodium ion or a cesium ion? And so look at your periodic table, right? And so our size, our atomic size is increases to the left and increases going down. So our cesium is going to be larger than our sodium. Right? So this one's larger. And who's larger, fluorine or chlorine? Chlorine. So when we have those molecules coming together, who's going to be farther apart? Our cesium and our chlorine, or our sodium and our fluorine? So which charges are farther apart? Sodium and fluorine or cesium and chlorine? Right? So it should be our cesium and our chlorine. And we can kind of think about this because our sodium would be one size. Let's say that it was a 1 across, and our fluorine was one size, and let's say that was a 2. Our cesium, it's got to be bigger than our sodium, right? So let's say it's 1.5. And our chlorine, well, it's got to be bigger than our fluorine. Let's say it's a 2.5. Right? So the total distance between those charges, this might be 3. The total distance between these charges is 4. So because cesium and chlorine are both bigger than the sodium and the fluorine, then there's going to be more distance between them. So if this R squared value has gotten larger, how is that going to impact the force? Is it going to be stronger or is it going to be weaker? So as R squared goes up, then our force is going to go down. So it's going to be weaker. So when we look at this, who has a higher melting point? Is it our sodium and our fluorine, or is it our cesium and our chlorine?
The cesium chlorine.
The cesium chloride, right, is going to be weaker than our sodium fluoride. So lower melting point, is that stronger forces or weaker forces?
Weaker.
Weaker, right? And so if you wanted to do that explanation, you could say something like sodium fluoride and cesium chloride are both ionic solids with ions of +1 charge and -1 charge. The larger size of both the cesium cation and chlorine anion compared to their counterparts in sodium fluoride creates a weaker ionic bond in comparison. This leads to a lower melting point. And so the things that we wanted to address is we wanted to address that they're ionic solids. Oop, that's a bad color for that one. Just to at least highlight why or what's holding them together. We're going to address why it's a weaker one. It's its larger size. But we also wanted to address that their charges are the same. And because it's a weaker ionic bond, then that lowers the melting point. Right? So you kind of tie all those things in together to give and provide an explanation. So sometimes what I see is you might know the end result. You might be able to tell me that cesium chloride is less, has weaker forces, but you might not be able to explain why it's a weaker force. Right? And so sometimes that's the part when you have these questions where you have to like write out an explanation, is make sure that you answer the why, not just the what. Right? So same thing on like your quiz. Sometimes what I get is I get the what, but I don't get the why. Right? So you might tell me that this molecule will do this, but you don't explain to me why, even though the question is asking you for which of these is going to happen and why does it happen that way. Right? So you just want to make sure that you guys are always addressing that why part. You guys have any questions on this one?
Looks good. Thank you for the refresher.
No problem. Now, we can keep going with these, or we can go into a different topic, right? So we could do these last two ones, but they're kind of all similar to what the other ones are. So if you guys want to jump to a different type of topic, we can also do that as well.
I did kind of want to do a bit of molecular orbital theory, but at the same time, I feel like this chapter is good too. So I guess either one of those.
Okay. So maybe we'll just try one more and then we'll move on and we'll do a little bit of MO, right? So let's look at this one here. All right. So I'm going to give you guys a minute so that way you guys can kind of get a head start on this one. And so I want you to try to answer this, right? Why does SbCl3 have a measurable dipole moment, whereas SbCl5 does not? And so Sb is antimony. Antimony chloride or antimony trichloride versus antimony pentachloride. One of them is going to have a dipole moment and the other one doesn't. So I'll let you guys kind of get started with that part. And I'll give you guys probably about 3 minutes or so. So if we're trying to answer this one, what's the first thing that we need to do? Where is your starting point on a question like this?
Lewis structure.
Lewis structures, very good, right? So anytime that's asking about dipole moments, Vesper geometries, bond polarities, right? You gotta do your Lewis structure because we have to know how things are connected, right? And so for SB, oh, wrong one. For SbCl3, how many valence electrons does it have? 26, very good. So we should have this antimony in the middle, then we have chlorine, chlorine, chlorine. And then for SbCl5, we now have 40. Right? So is there anything special about these Lewis structures, or are they just all single bonds with a whole bunch of lone pairs around each of the chlorines?
the one on the left should have a lone pair on the central atom.
All right, so we should get a lone pair on the central atom. Great. Okay. So for the antimony trichloride, is there anything, or what electron geometry is this one over here on the left going to have?
It's not tetrahedral. Trigonal, is that trigonal? What is it? Trigonal something. Let me take a look.
What is the difference between electron geometry and molecular geometry?
Oh yeah, it is tetrahedral.
Right? So electron geometry treats them all the same, whether they're lone pairs or atoms, they all get counted. And so there's only a couple options for electron geometries, right? It's linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Right? Molecular geometries is where they start to take into account that their lone pair is there, and it names it differently. So it names the shape that would be there if we couldn't see the lone pair. And so that's where you get linear, you get bent, you get trigonal planar, you get another bent, you get tetrahedral, trigonal pyramidal, another bent, you get trigonal bipyramidal, a seesaw, a T-shaped, and then you get linear, right? And then you get octahedral, square pyramidal, square, planar, and then, oh, what's after that? I think we're back to T-shape, and then we're back to linear, okay? So electron geometries are always our basic ones, right? So it's tetrahedral for the one on the left. What about the one on the right? What's this electron geometry? Trigonal bipyramidal. And so it's saying that the one on our left, was it polar or non-polar? Right, so if we go back to our question, is the one on the left polar or non-polar? It's saying that it's polar. And it's saying that this one is non-polar. So how would you explain that? How would you explain that this one on the left is polar versus the one on the right is non-polar?
Lone pair. Well,
What
actually,
about the lone pair?
it's more actually of the lack of the lone pair. So, well, don't you have to do those arrows with the cross on it?
So we do have to do the dipole, right? The bond dipoles. Yeah, you can do that, right?
So
And so if you do your bond dipoles,
going down, isn't it? It's actually going down, not up.
I'm sorry, what was that?
Is it? I actually thought it was going up. It actually should be going down.
So in reality, just adding them to a Lewis structure is that good enough? Or what do we really need to do if we are trying to figure out if something has a dipole moment or not?
Don't you need to add them all up?
Right? So we need to add them up, but we need to draw this in its three-dimensional shape, right? Because the one going to the left and the one going to the right for this one over here in the trichloride, those are not actually canceling each other out all the way, right? And so you need to take into account their three-dimensional shape. So really, we should take these and we should redraw them so that this looks like a tetrahedral.
Mm-hmm.
And then we can add those in. And then we would have our lone pair or dipole moment going down, right? The one on the right, we would have our axial positions, and then we would have our equatorial positions. And then you're right that this one here, all of their bond dipoles cancel out because they're balanced or from their bond angles. And so because they're all canceled out, then this is going to have no dipole moment. And so you want to say this one here is trigonal bipyramidal. And because of the position of all of the chlorines, their bond dipoles are going to cancel out, and so it will have no dipole moment. So you want to include the name of the shape there, so that way people know what's going on. And then you could say that this one, it is trigonal pyramidal. And then the bond dipoles for the chlorine don't cancel out. Because they don't cancel out, then it's going to have a dipole moment.
Do you care about the direction of the dipole?
So the direction of the dipole depends on how you draw it, right?
Yeah, I was just about to ask, are you strict on the drawings too?
So you should be able to draw them, right? Because if you don't know how to draw them, it can be hard for you to tell whether they're going to cancel out or not, right? So that is the caveat to that. However, I also recognize that you guys are not becoming artists, right? So I'm not judging you on the quality of your drawings, but they do have to be legible, right? In the same way that if you write things that I can't read, I can't give you points for it. So if you draw a structure that I can't tell what is going on to it, I can't give you points for that, right? So you do want to make sure that you can draw them to be legible, even if they might not be your most perfect angles.
What I'm asking is because on this left side, this one has to be moving to the left. I mean, moving down, if I'm not mistaken, because actually on this, your chlorine that's in the back, shouldn't that be pointing down instead of to the right?
Yeah, so it should be down and to the right. And so it looks like, oh, too many of those.
Wait, that's a, hold on, let me see.
Right, so this is what we're trying to make.
Yeah.
Yeah, right. And so it should be down and to the right, which is why it's kind of going down and to the right. But yes, it is not the best drawing in the world, but that's also okay. It's also why you use your wedges and your dashes to give you that concept.
Okay.
So,
And is that last blue arrow, that's the one you're indicating the direction of the dipole, right?
yeah, so this one down here is kind of giving you the idea about where your dipole moment is for your molecule, right?
Okay.
Because in reality, it should be starting at the center point where our central atom is, and then it should be moving from there.
Yeah.
Yeah.
So we're expected to draw the dashed lines and stuff.
So you should be able to express your molecules in 3 dimensions, right? So if you need to tell me that this one's going into the page, then you should know how to do the wedges and the dashes. So lone pairs don't get an arrow because lone pairs aren't separate from that central atom. And so you don't want to think of them as having pull on the central atom because they're actually just a part of it, right? So instead of it really being pushed up and away, this lone pair kind of really just sits right here on top of that central atom, right? So lone pairs don't get it because they're all part of that. So I wouldn't be too stressed out about drawing 3-dimensional shapes, but I would recommend that you at least try some of these things. So that way, if you get a 3-dimensional drawing, you know how to interpret it, right? But I do understand that you guys are not becoming artists. So normally I'm not trying to ask you guys draw the most perfect tetrahedral. That's not normally the goal. But I would say that where people run into problems is when they start to do their Lewis structures and they just start to like list things like this. And they tell me that this molecule is nonpolar, right? And they say it's because everything's balanced. And in reality, they're not balanced, right? Because they don't look like this. The shape of this molecule is not going to be a square. The shape of it is going to be a tetrahedral. Right? And so there's a difference there.
Because of the 2 different elements.
And so in the molecule that you draw it like a Lewis structure where everything's 90 degrees, it looks like the fluorine should perfectly cancel out with the other fluorine. But in reality, when you have a molecule that's in its tetrahedral shape, one of these does not perfectly cancel out with the other because they're not 180 degrees apart from each other. There's difference.
Would we be able to like memorize this in our heads? So, because
What do
I
you
mean,
mean?
we won't be able to have that website in the test, you know? So, like, how would we be able to really differentiate it on paper rather than having a
So
that
you would
the
need,
website really does help.
so you have to be able to draw them, right? And so that's where it comes from, is being able to know that a grouping of 4, what does its basic shape look like, right? So
But like is what I'm saying, that we've learned how to do that basic shape. The one that I kind of just remember is doing that basic shape. The one that you said that would be wrong. But I don't really know how to put it into the next shape, which is the one right next to it with the dashes and stuff, without looking at the program to help. The program really does help, but I'm
So
saying I don't know how to look.
I get what you're saying. I think that the thing is basically you kind of have to memorize what your shapes look like coming up next, right? Because in the same way that,
a good way to memorize it.
so just like in your slide packs, let's pull it up. There is a chart that has them, right? And so let's see.
Professor Lau, don't you have the little play sets where it's like you have the little balls and the sticks where we can play with that?
So we
might
did use those, right? So you guys in the Monday, Wednesday class, because of the holiday, then you guys didn't get the opportunity to come into lab and to use those sets. But yeah, you can do it with the model sets. That's fine. The only thing is that you won't have model sets during your exam, right? So there's that part. And also having the model set during the exam doesn't necessarily solve that issue because you still have to know which one to, oh, I'm looking at the wrong chapter here. You still have to know what your next shape is going to be, right? So you still have to have that part. But there was a chart, right? That's in your slides. There's also like a handout that you could have printed, right?
I think the play sets might make it a little easier. I don't know, Megan.
Yeah.
I think for me, when I started learning about it, playing with those makes it a little easier to visualize where everything is located.
Right. And so this slide, right, which is from your very first chapter 10, right, the first Vesper one, has all of your different shapes, right? So as long as you know how many electron areas there are, so that's your number of electron groups. Oh, sorry. There we go. So as long as you know how many of your electron groups you have, then you know what their basic shapes are. And so you're basically trying to memorize these 5 things over here on the left.
By the way, Professor Lau, you want us to remember this whole chart for the exam?
You
Or
do
is
need
this-
to know this whole chart. Right?
What other charts are we supposed to memorize for chapter 9 and 10?
So you should know all of your electron geometries and your molecular geometries, right? You should know how to figure out your hybridizations, right? Your other charts is that for these, you should have your bond angles, right? So that means that you know that trigonal planar. What would this bond angle be for trigonal planar? What do you guys think?
120.
120. Right? The trickiest one to remember is that for a tetrahedral, what is that bond angle?
109.5.
109.5. Right? You need to know your intermolecular forces. So you need to know the 4 different types of intermolecular forces. You have London forces, dipole-dipole, hydrogen bonds, ion dipoles. Right? You should be able to classify your different types of solids. So that's your metallic solids, your ionic solids, your network covalent solids, and then you would have your other types of your molecular solids. So that's London forces, dipole-dipole, hydrogen bonds, right? And so you should know all of those.
Do you have that chart for us for the metallic solids and the different classifications of all the various?
So there is a chart, right? So just like in this one for chapter 10, there's going to be one for chapter 11. So it's not true that dipole moments don't start until you're tetrahedral, right? And that's because you can be trigonal planar. And if you're trigonal planar and you have a lone pair, then you can become bent and you can have a dipole moment. You can also be trigonal planar and you can have different bonds there and you can have a dipole-dipole. Even a linear molecule can have a dipole-dipole because, excuse me, you have two atoms there. And so if they have different polarities on their bonds, then that's an option as well, right? So it's not just tetrahedrals.
Thank you. Just
So I know you mentioned that we should be able to like draw the actual molecular structures.
Mm-hmm.
I kind of feel like I'm pretty I have a pretty good grasp of like, okay, so say if I had a like a one that was electron geometry, like trigonal bipyramidal, just for example, and then
Mm-hmm.
if I wanted to add like lone pairs to that, I kind of feel like I have a good idea of like, you know, where the lone pair should go just by like
Good.
kind of thinking about it. But
Mm-hmm.
I guess would it still be like required in like an explanation to have an actual drawing? I mean, it's probably a good idea.
So,
I'm just asking if it's like
so
required.
you don't necessarily have to, well, okay. I could ask for that. Generally speaking, I probably wouldn't ask for you just to do a drawing, right? But I might ask for you about why is it like a seesaw instead of something like a trigonal pyramidal shape, right? And so you would want to make sure that you could express that, right? That you could explain why. And sometimes it's easier to draw a picture to do that explanation than it is to do all of that in words, right? And
so you could actually just draw a picture and then
well,
it would.
You couldn't just draw a
Oh,
picture, but
okay.
you could draw a picture and then use some words to explain it, rather than trying to say like, well, if you compare this flooring with this placement of that flooring, and then it would have to require a lot of words, right? But you
Yeah.
could just draw the picture and say, right? And you could say that having your lone pair at the equatorial position, as shown in the picture, has fewer London bond bonding pair repulsions than if you were to put it at the axial position, right? Because it's 90 degrees away from only these two instead of being 90 degrees away from these three, right? And so that's a little bit simpler than trying to go through and trying to express all of that in words, right?
Okay.
So that's where a picture can sometimes save you some work or just help you clarify instead of relying only on your words to express that.
Yeah, because I think if you asked me that question, I would probably say like the reason it's seesaw is because those the axial positions are the two on the top and bottom, right?
Yes, right.
Yeah,
So
so
this
I
is
would have
axial.
yeah, I would have like said something like, okay, the equatorial positions have greater bond angles. So if the lone pair goes in an equatorial position, then it'll like reduce the repulsion just because it's in that like greater angle spot.
Yeah. And so that could be okay because you
yeah, and then that gives it the
terms to
seesaw
express
shape.
it. Yeah. Whereas
But
like
I mean, I could see where like drawing it would probably help.
Yeah, especially if you forgot the terms axial and equatorial for your exam, right? And if you couldn't remember what the name of that position was, you could draw it and then you could say, as you can see, this positioning of the lone pair would be better than the other positioning of the lone pair because, and then you would do the explanation, right? So
Yeah.
they are tools to help you explain things. I'm not as concerned with just draw it for me, but I do think that it is helpful in explaining things, right? So that's where I'm encouraging you guys to know how to draw them, not because I want you to be expert artists, but because I think that they are a useful tool in explaining things, right?
Yeah, so the ultimate goal really is to just like get across the fact that you can understand why things are happening.
Exactly, and to get across their polarities in 3 dimensions, right? Because that's the limit of Lewis structures. Lewis structures are all 2D, right? Molecules are 3-dimensional. Right? For your question, Tiffany, this one down here, this HCN, right? H has an electronegativity of 2.1, carbon is 2.5, and nitrogen, I believe, is 3.0. Right? So what electron geometry or molecular geometry does HCN have? What is its shape? Right, so anyone can answer that. Linear. So it's linear. And so when we look at each of those bonds and we start to talk about its bond polarity, between hydrogen and carbon, which direction should that arrow be going?
To the left,
So is it going from the carbon to the hydrogen or the hydrogen to the carbon?
carbon to the hydrogen.
So it should be going from the hydrogen to the carbon because our carbon is more electronegative, right? Its electronegativity value is higher. It's 2.5 compared to the 2.1, right? So we should be going to the right. On the other side, between carbon and nitrogen, which direction is that arrow going?
It'd also be going to the right.
Also is going to the right. So it's also going from carbon to nitrogen. And so roughly those arrows are almost the same length. The one going from carbon to nitrogen is maybe a little bit longer. But as an entire molecule, would you guys consider this to be polar or non-polar?
It's definitely polar.
So it's definitely polar, right? Because when you think about it, this hydrogen is kind of positive and this carbon is kind of negative compared to it. And then it continues to shift even more between that carbon and that nitrogen. So kind of like these arrows, they're not working against each other. They're kind of being added up with each other.
Would it be an ionic bond?
So it is not going to be an ionic bond because their differences are still not from carbon to nitrogen or from hydrogen to carbon. They're not more than 1.7. So there's still covalent bonds, but there's just a separation there, right? And so let's see if we can build this here. Oh, come on.
Will we be giving the electronegativity?
So if you needed the values, I would provide you with the electronegativities for them, right? So it's either going to be, I'll give you the entire chart, kind of like you guys got on that one quiz, or I would give it to you and you guys would just have the values for it, kind of like on this most recent quiz, right? So they kind of go both ways. It kind of depends. Sometimes I don't want you guys having to search through all of them to try to figure out their electronegativities.
By the way, will the bond enthalpy chart be provided also?
So if you need the bond enthalpy values, then I would give you those bond enthalpy values, right? So you don't need to memorize bond enthalpies. That would be crazy. But if I gave them to you, you should know how to use them, right? Which also means that if I give them to you, you should be able to solve them with just the ones I give to you, right? So you shouldn't need additional bond enthalpies. So just keep that in mind. Now,
thank you.
This is one thing for us to look at when we think about polarity, okay? So if A and C are the same, you can kind of see how there's no molecular dipole here, right? But if one is not quite as electronegative, you can see how their bond dipole has become unbalanced. And so that's how this entire molecule can kind of get this molecular dipole, which is to the right. So I'm going to set one up. I want you to tell me whether there's going to be a dipole there or if there's going to be no dipole there. So do you think that this molecule, is it going to be polar or non-polar? polar. Now, which direction do you think is it going to have a dipole?
Carbon, I mean, the C to the B,
When you go from where to the where?
C to the B.
Right? So are you thinking it's going to go from C up towards the B?
Yeah.
Right? So if we look at the direction of the arrows, right? This one is pointing to the right, and this one is pointing to the right, right? So do we have anything pointing back to the left?
No.
No, right? So we're going to definitely get something going towards the right-hand side because both arrows are kind of going in that direction. Right? Now, one is going up. Is the other one going down?
Mhm.
Yeah. And so they're kind of working against each other in that regard. So we're not going to see as much downward movement, but maybe we'll see a little bit, right? And so one way that you can kind of think about this is if you add this arrow to the end of this arrow,
Yeah, it's
the
just about.
start of one and the end of the other kind of gives you an idea about where they're going to be going. So our dipole moment is going to look something like this, roughly. Which is what that yellow one is looking at, right? And so you're right. This is called vector addition because when we add the little hash on it, it's called a vector. And so your goal for molecular polarity is basically you make all of these vectors and you just smash them all together. You add one to the end of the others, and that entire overall process will eventually lead you back to where your dipole would be.
I just learned what a vector is in microbiome. Now I have to learn it again.
Well, it's a good thing then you learned it because it's the same, right?
It's from animal to host for microbiome.
Oh, for that kind of vector. Yeah, no, this is a different vector. So for this one, right, you can see how if we took this arrow and we added it to here, that those two would end up canceling themselves out, which is why we have no molecular dipole, right? And so for bond polarities, for dipole moments, you're really trying to draw these bond polarities as vectors, and then you're adding those vectors up to get an overall process, right? Sometimes I think that people get scared about that because vectors seem like a really complicated math, but they're really just looking at whether there's any overall movement from one to the other. All right, any questions on that part? So knowing whether something is polar or non-polar will definitely be on your exam.
Oh.
All right. So Michael has been waiting patiently, dying to hear about molecular orbitals, right? And so we're going to talk about this a little bit. Vector addition itself, not what I'm concerned with, right? So vector addition is not like I'm going to say, oh, you have a vector going this way, you have a vector going that way. What's the added vector? But I might just ask you, right? Is this molecule polar or non-polar? And vector addition is kind of what helps you find that out. All right. So molecular orbital theory. All right. So let's talk about this for a second. So the first way we started to model atoms was our Lewis structures, right? Now, Lewis structures were good at showing how things were connected, but they didn't succeed because they couldn't tell us the 3D shape. We also started to model how electrons were inside of the atom, and that's where we came up with those original S, P, D, and F shapes, right? And so our S1s were spheres, our P1s are our dumbbells, right? Our D1s kind of have those 4 different lobes on them, and then the F1s started to get real crazy, right? But when we started to build these molecules, we started to see that they did not line up well with their shape, right? And so how did we account for that change, that our bonding didn't look the same? Oh, there we go, flower. I like that explanation. Right? And F1s I just give up on drawing because honestly, they're crazy. So how did we start to account for molecules not having these exact shapes, right? How do we account for things like trigonal planar or tetrahedral? What did we start to do with these orbitals?
Are you referring to the spinning?
So not necessarily the spinning, right? Because that's the positive spin and the negative spin and the
fan.
quantum. Sorry, what was that, Megan?
Fan.
So not the fan, right? But how did we start to account for the fact that for something with 3
Lemon?
electron groups,
I don't know.
for 3 electron groups, it looks like trigonal planar. But if we look at all of our orbitals, none of them take on that orientation. None of them would have 3 different orbitals 120 degrees apart from each other. Hybridization, very good. So we started to say, okay, maybe when we form these bonds, those molecules, they mix some of these orbitals together and they come up with these new orbitals, and that was our hybridization. So when we hybridize, if we have 3 electron groups, what would a hybridization be?
SP2.
SP2, right? And so hybridization was one way that we started to answer this, right? Is that we started to mix them together in order to get the experimental shapes that we started to see. So SP2 is trigonal planar. What shape does SP3 look like?
Tetrahedral.
Tetrahedral. What about SP3D?
Trigonal bipyramidal.
Trigonal bipyramidal. Very good. So that was one part. And so they started to do that. And it does a good job at explaining shapes, but it ran into a problem. And it ran into a problem for something like oxygen. Now, with oxygen, we think of that as being a double bond between oxygens. And so if we look at the orbital diagram for oxygen, that's 2s, 2p. Right? And so we have 2 of those together.
What would octahedral's hybridization be?
Well, that's a good question. So how many electron groups do we need for an octahedral?
SP3D2?
SP3D2, right? Because we need 6 of them. And so SP3D2 would always lead us to an octahedral. Very good. All right. So if we form a double bond, we're thinking that we're going to share 2 electrons from our oxygens. And so that would fill in these 2 orbitals here, right? Those green arrows. So would you think that these oxygens have any unpaired electrons?
No.
No, right? We would think everything was paired up. However, what we started to experimentally find out was that wasn't the case, right? And so they had to come up with a new theory to explain this.
Wait,
And so this is where we come up with molecular orbital theory. What was your question, Edward?
I remember this. Isn't oxygen one of those special? It's not just oxygen. I think it's like nitrogen is also one of those special.
So there's a lot of them, but basically they are the reason why we had to start doing. Oh, I see where I run. Why we came up with this new theory, right? And so the idea with molecular orbital theories is instead of those electrons belonging to one atom or the other atom and things like that, they said, really, you have this molecule and those electrons are going to take up all of the different spaces inside. And so they don't really belong to one atom or the other. You just kind of have a whole mixture of electrons in there, and they're going to take up this different space. But we don't really know whether the electrons came from A or B or whatever atom, we just know they take up all of this space. So it's this idea that your orbitals kind of belong to the whole molecule instead of only being on that oxygen, only being on that other oxygen. And so it takes these diagrams that we've been like working with and being familiar with, and instead it mixes them all together into orbitals that would belong to the entire molecule.
Isn't this
So,
where sigma and pi bonds and all of that comes into play, I think.
So sigma and pi are a part of this, but sigma and pi also come from before, right? So sigma bonds is anytime you have a single bond, double bond, or triple bond, the first bond is always sigma, the second bond is always pi. But yes, we also see those in here. So on your exams, what I would give you is I would give you these orbital boxes, and I will also draw out what the molecular orbitals look like, right? And so the concept for this is that while this is one of our oxygens and this is the other oxygen, when we mix them, that first bond that we make, that's going to be a sigma bond for the 1s, and then there's also going to be an anti-bonding for the 1s. And so the bonding one is a lower energy than being by itself. The bonding one is a lower energy. The anti-bonding is a higher energy. When our 2s mix, we can mix those together. And in this case, for our oxygen, we're going to start with our we have to do our 2s first. So for our S1s, we're going to have a sigma 2s and the anti-bonding sigma 2s. Hold on. I'm going to make some more space here.
And so this is using their full electron configuration.
So this is using, this picture is not good enough quality. One second.
No, we can see it. We can see it.
All right. So the idea behind them is going to be that when we mix them together, all of these boxes that are on the right side or the left side, they're all going to show up as an option in this middle part. But the option is either going to be whether they are bonding or whether they are anti-bonding. So the lower energy ones are always the bonding ones. The ones with the little stars are always our anti-bonding, and they take more energy. Does anyone have any questions about that part?
What exactly is an anti-bonding like orbital?
So an anti-bonding orbital is an orbital that takes more energy for us to put those electrons in there than if they were in their ground state. Right? So when you form these orbitals, some of them, their interference is not as big, so they're going to be a lower energy state. And some of them, because of their electron-electron repulsions, it's going to be a slightly higher state than if they were by themselves. Right? That doesn't mean that the higher state can't occur. It just means that they are less likely to occur. And so when we form a bond, sometimes the benefit we get from forming the bond outweighs the downfall of having some in the anti-bonding, right? So it's like this balance that you have. So if you only had bonding, that would be best. But sometimes we would rather have bonding and some anti-bonding than just no bond whatsoever. So this is a part of sigma and pi, right? What I would say is sigma and pi kind of exist separately, but you also see them here as well, right? So a sigma bond and a pi bond and what they are is different than just where we see them in our orbitals, but molecular orbital theory still retain the same type of meaning for sigma and pi.
I'm still confused on like how you did this. Like,
so for your class, you guys won't have to draw in these boxes, right? I would basically present you this set as you guys would have it, right? Because I get that drawing all the boxes, knowing which ones are different energies is tough, right? So you wouldn't have to draw the boxes, but you would have to be able to label them,
Thank
Okay.
you, Professor Lau.
So what you need to be able to do is you would need to know which orbitals were being used, right? And so your lowest energy option is going to be your first orbitals. And so where do we start for our orbitals?
The 1s.
The 1s, right? Now, if it just said your valence ones, then we might just only show this top ones, and then you would have to look at your atom to know where its valence had started, right? So read the wording on the diagram before you just start filling things in. And so we know that if there's only one box, it's always going to be your S's. If there's 3 boxes, what sublevel is it going to be?
The P's.
The P's. If there's 5 boxes, what sublevel is it going to be?
D's.
D's.
D's, right? And if you had 7, it would be F's, but you're not really going to ever see those, right?
Professor Lau,
Mhm.
can you briefly go over, like, say, oxygen O2 for us to take a look at it? I can't even.
That's what we're going to do.
Oh, we're about to do that? Okay.
So this is going to show us a bond between 2 atoms inside of that molecule, right? So on one side is going to be one element. On the other is going to be another element. So if we're looking at this O2 bond, then these blue ones, you want to fill in like it was just that oxygen, right? So if we wanted this to look like our oxygen, how many electrons would we have in its 1s?
It's filled. So
It's
up and
filled.
down.
So 1 up, 1 down. And for its 2s,
It is also filled.
1 up, 1 down. Good. And what about for the 2p?
It should be 3 up, 1 down.
Right? So we should have 1, 2, 3, and 4. Okay? And so that's one of those oxygens. On the other one, we would also have our oxygen. So we could have 1 up, 1 down.
Mhm. Yep.
1, 2, 3, and down. Okay? So now we need to make the molecular orbital, so the one in the middle. And so what we're going to do is we're going to take all of the electrons that are on the outside and we're going to put them into the middle. And we're going to see which of these orbitals we would fill in. So we have a total of 8 electrons from the left and 8 electrons from the right. So how many electrons do we need to put into those yellow boxes?
You fill the yellow boxes on 1s and 2s.
Well, so how many total electrons do we need to put in there first?
8.
So there's 8 from one oxygen, but there's another 8 from the other oxygen. So total, how many electrons are going in the middle?
Oh,
Mhm.
16.
We're doing 16. So we just start from the bottom and we just add in electrons as we work our way up, right? So we go 1, 2,
Up and
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so filling them in is really not that hard, right? It just feels more daunting than it really is because it looks complicated.
So Professor Lau, I was also asking about, there are special exceptions. So I remember doing MOTs where sometimes where let's say the pi 2p would go below the sigma, the anti-bonding. So there are some exceptions where they.
So the placement of these depends on your electronegativities, right? And so we're not going to worry about that for this class. I'm not going to make you guys draw in these diagrams so you don't have to remember when is the pi anti-bonding first and when is it second, right? So I'll give you the boxes in the middle because I don't think that it's worth it to memorize all of those. But yes, basically this center diagram looks different based on which elements are involved in that bonding process.
And so we might have to draw those boxes on the side, right?
So you would need to be able to label all of the boxes, right?
Oh,
so
so
if
you
I
wouldn't-
gave you the boxes with no labels, you should still know enough to be able to fill in what those labels are.
So you wouldn't even need to draw the side boxes unless, I guess, if you wanted, but like it's just you'd have to label these boxes and then
So how about this? Let's
fill
finish
them
this
in.
part first, and then I'll give you guys an example of what it would look like for like if I gave you nothing, right? And
Okay,
then we
sounds
can go
good.
from there. So this is what our O2 looks like. And so when we talk about bond order, right? Bond order is your number of electrons in your bonding minus the number of anti-bonding electrons. And then what else do we need to do for our bond order? Do you guys remember?
Sorry, what was the question again?
So for this one, we have our number of bonding electrons minus the number of anti-bonding electrons. And so if we're trying to find the bond order of it, what else do we need to do? What's the second part?
Don't you divide it all by 2, I think?
We just need to divide it by 2. So bond order, it's measuring the same thing that we used to measure with the resonance ones. This one's just a little bit different because instead of doing all of our resonance structures, we're really just talking about them as being bonding or anti-bonding. Right? And so we're going to divide this whole thing by 2. So now I need to get back to that page.
So so the bond, when you do the resonance, you do that when you're doing the Lewis structures only?
So for molecular orbital theory, there's no resonance anymore because they are treating them all the same. So you don't really see resonance because they kind of all get associated as just being one giant molecule, right? So you do not need to worry about resonance when you do MO theory.
So for the bond order for the Lewis structure, is it the same?
So bond order for Lewis structure follows a different equation, and then you have to deal with resonance. Bond order for molecular orbital theory, you don't need to worry about resonance because you can't really tell the difference between whether that double bond was between one oxygen or the other. It doesn't matter anymore.
Oh no, I meant like the numerator part is the same, but the denominator is different.
Both are different, right? So bond order for your Lewis structures is a completely different equation, right? It's your bonds from each of the resonance structures divided by your number of resonance structures. So it is a different equation, even though you guys are talking about the same thing.
Okay, thanks.
So for this one, how many bonding electrons are there? And so that's where you look at the bonding orbitals and you count how many electrons are in there. Right, so we have 2, 4, 6, 8, 10. Very good. How many anti-bonding electrons do we have? So if we only had 4, then we would only have 14 electrons, right? But we should have
I'm sorry.
16.
6. Sorry.
6, right? And that's
I haven't
2,
read the cap.
4, 6, right? So we have a total of 6. So the bond order for this one becomes 10 minus 6, so 4. 4 divided by 2, and so the bond order is 2. Now let's say that instead of being O2, it was O2 minus. So we have one more electron in there. So that electron would go up here. That is going to update our bond order, right? Because instead of being 6, we're now 7. And so would our bond order increase or decrease? what is our new bond order if we are O2 minus?
1.
That doesn't seem quite right, right? Because 10 minus 7 is 3, and 3 divided by 2 isn't 1. What would 3 divided by 2 be?
1.5.
1.5, so it'd become 1.5.
Right.
Okay. So the more electrons you have in the antibonding orbitals, the lower your bond order becomes, right? And the lower your bond order, the longer your bond is, the weaker your bond is, right? And so this is where you can kind of look at whether or not a molecule should exist or not. Because if you have all of these filled, right? So if we have 10 bonding electrons and we have 10 anti-bonding electrons, our bond order becomes 0. Is there any reason why it should form this bond?
If it's 0, that's then no, right?
No, right? So if your bond order ever becomes 0, or if it becomes negative, which really shouldn't happen, but if it became negative, then you really don't want to form that bond. It means that there's no energetic reason, there's no benefit for forming it. But let's say if you're even just 1 short of this, if it's 10 minus 9, then you would have a bond order of 0.5, and you would still want to form that bond, right? It's just going to be a weaker bond because there's not that much energy gained from it. If you have a lot of bonding electrons compared to your anti-bonding electrons, no, 4, then that bond order could become a lot bigger, and then you have a shorter, stronger bond there. And so that's what your MO theory is telling you, is looking at these 2 atoms. What does that look like when you form them? So we're going to try an example of this, right? So I'm going to grab a copy of this chart from one of our other ones. And we're going to look at this. So we're going to fill this in. Let me just find a space for it. How do I crop you? Here, well, let's just take this part out, and then we're gonna block these. All right. So it's not the subscript of the element. You're dividing by 2 because each bond is 2 electrons. So we have our molecular orbital diagram here. What we're going to do is we're going to mix our silicon with our phosphorus. And so we're going to be looking at our valence electrons inside of our MO diagram. Right? So one of these should be silicon and one of them should be phosphorus. And we want to find the bond order of it. Okay. So for each of these, we should fill in what that box should be. Right? So imagine that there was a line under each one. We should be able to fill in what that box is trying to stand for. Okay.
So first of all, during the
Mhm.
exam, this would be like a question for us.
So this would be like a question.
So all we have to do is fill out, looks like, so the elements, the hybridization, and then figure out how many goes into the sigma bonds, how many goes to the pi bonds, and what goes into the anti bonds. That's all we need to know.
Well, and then you have to figure out your bond order from it. Yeah.
And bond order. I'm sorry. And is it
Right.
valence electron or is it all the electrons?
So it could be either one. This one, we're looking at your valence electrons. Right. So let's go ahead and we'll put silicon over on the left, and we're going to put phosphorus on the right. And so what I would recommend is go ahead and start by labeling your boxes. Right? So for silicon, what's its electron configuration?
Like the total or just for the valence?
So let's do with the shorthand. What's the noble gas electron configuration?
Neon with 3s2. So it's silicon. And then it should be 2p2. Yeah, 2p2.
That doesn't seem right.
Is it? I'm sorry, 3p2.
3p2. All right. So when we look at these boxes, what should this bottom box be labeled?
3s2. Wait,
Right.
3.
So if we're looking at the valence, right? So our valence is going to be the ones that start with the 3. And so our bottom option should become what?
And that's still 3s.
Yes. All right. So the reason why we're doing valence instead of all of them is if we did all of them, we would also have to do all of those molecular orbitals for the 1s, the 2s, and the 2p. So it just becomes this huge thing. And all of those core electrons don't matter. They're all going to cancel out. So that's why normally we can either do valence. Sometimes when it's just 2p, right, then we might do it from the beginning because the 1s is not that much bigger. Right? So this one up here is going to be our 3p.
So for these, we always use like the shorthand configuration, basically.
So you can use your shorthand configuration, right? Because we're not worried about core electrons. So whenever it's talking about your valence electrons, then you can use your shorthand because your core electrons are never part of your valence.
Okay.
Now, as long as we're thinking about silicon, let's just fill in its orbital diagram. So this one on the left, the 3s, what should that one look like?
Filled.
Filled. So we should have one up, one down. And the 3p?
The first one filled.
So it should look like this.
And then have
I was looking at phosphorus. And they
Well,
all
let's finish silicon first, right? So what should our 3p look like for silicon?
just the first two boxes have one electron.
Right, the first two boxes have one electron. Okay. So down here, this blue one, what should that one be labeled for our phosphorus? So this one down here, what should its label be?
3s.
3s, very good. And up here,
3p.
3p. Now, for its boxes, how many electrons should it have in the 3s? Right, it should be filled, good. And the 3p?
One electron for each box.
One electron for each box. So 1, 2, 3.
why?
What was that?
Why?
Why what?
Why 3 on the 3p?
All right, so the electron configuration for phosphorus, what is its electron configuration?
3s2o 3p2.
Is it 3p2 for phosphorus?
No,
So what is its electron configuration?
3p5.
So it would be neon, it would be 3p2, or sorry, 3s2. And so you think it's 3p5. Was that what you said?
It would be neon and then 3s2 and then 3p3.
3p3, right? And so that's why it's got 3 electrons in the 3p.
Oh, okay.
Okay, good. And so now let's start to fill in from the bottom on up for those molecular orbital theories, right? So whenever you have one box, what kind of bond is that going to be? Is that going to be sigma or is it going to be pi?
Pi.
How many different pi bonds can you make?
3, 6, 9,
Right?
2.
So we can make 2 pi bonds. And how many sigma bonds can you make?
No.
Does someone else want to help her? How many sigma bonds are there?
1.
1. So there's always only 1 sigma bond and 2 pi bonds. Right? So if we only have 1 box, is that going to be sigma or is that going to be pi?
Sigma.
Sigma, right? So this first one, whenever there's only 1 box, it's always going to be sigma. Now, is this going to be a higher energy or a lower energy?
A lower energy.
Lower energy. So is that bonding or anti-bonding?
Anti-bonding. Oh, bonding.
Right? So just imagine, you always want lower energy. So a bonding one that has lower energy, or sorry, an orbital that has lower energy is going to be our bonding. An orbital that has higher energy is kind of working against that. So that's going to be our anti-bonding, right? And so you're right. This should be the 3s sigma bond. And so what should this top one be labeled as?
What top one?
This top box here.
That'd
So
be
you
the
think-
anti-bonding one?
So it should be the 3s, but it should also be the anti-bonding. So you need that star there, right? So it's sigma star 3s, and that's your anti-bonding. Good. What about this first box up here?
Sigma.
So this one is going to be a sigma,
And that's right.
and that's, sorry, someone's actually calling my office. That's like never happened before. But it's fine. I'll call them back. And then the second box, this one up here.
You could answer. Yeah.
No, it's
Then
fine. Who knows? It's probably going to be spam. You know how it is. All right. So if this one's got 2 boxes, what kind of bond should it be?
Pi. 3p, and then I'm not sure if you put an asterisk or if you only do that on the.
In this
Like,
case, the star is only on the top. So do you see the 2 top rows? Those are your anti-bonding. So in this one, it's pi 3p. It's actually no star is needed because that one's the bonding. It's only
And it's when like the diamond part goes up is when you start doing that.
Exactly. So the anti-bonding, the star signifies the anti-bonding. And so that's when it's going up because that's when it's signifying that it's above the energy of the one on the side, right? When it's going down, then it's a lower energy, right? Because you kind of dropped down into it. When you went up, then you went higher. So you had to put in extra energy. So this first one here, is that going to be our pi or a sigma anti-bonding?
This first one where?
This one right here. Is that our,
Anti-bonding?
that's our anti-bonding, but is that pi or is that sigma?
Pi.
That would be our pi, anti-bonding 3p, and then this one would be our sigma, anti-bonding 3p. So how many electrons do we need to plug into this middle part?
Starting from the bottom.
Mm-hmm.
I think 5 more.
So how many total electrons are going to be in this middle?
4.
So there's 4 just from the silicon. What about the ones from the phosphorus?
So 9 total.
So we should have 9 total, right? So we're going to put in 9 electrons. So we can start from the bottom. So this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. You guys have any questions about that?
I thought you were talking about like how many would go into the top part.
I see what you're
So, sorry, go ahead first.
Okay, thanks. So the so like when you're filling in the electrons for the middle part, you want to kind of fill them in like from left to right. So you do one for the left and then like work your way down basically.
So
Or-
you fill them in the same way you've always filled in all of your orbital diagrams, right?
Yeah.
So everyone at the lowest level goes first, right? Each box only gets 2 electrons, so one's up, one's down. And then once you fill in that level, you go to the next level, right? When you get to a level that has more than 1 box, then everyone gets 1 before anyone gets 2.
Okay, makes sense.
Okay.
I'm a bit confused on why the 3p, since it was 3p3, then why is there only 2 arrows on the 3p? Or is it from the
So
other?
this one is silicon,
Oh,
this one is
okay.
phosphorus. Yeah. Okay. So let's look at this bond order here. How many bonding electrons do we have?
Seven.
7 bonding electrons. How many anti-bonding electrons?
2.
So we have 2 from this top one here. Good. And then we'll divide it all by 2 because that's how many electrons in the bond. And so this becomes 2.5. So should that bond occur?
Yeah.
Yeah, right? There's a benefit for it. And so this is going to be somewhere between a double bond and a triple bond in its
And this
strength.
would be a polar?
What was that?
Would this be a polar?
So this doesn't tell us about polarity.
Oh,
Right? Molecular orbitals are not necessarily about telling us about polarity, right? More what it's used for is something called magnetism. So if you are magnetic, what do we know about your electrons? So I think the term is paramagnetic and diamagnetic. What's it mean when you're paramagnetic?
that you can't. You
What do we
can't
know about your electrons?
connect to others?
I think it's like some of them are left unpaired.
Right? And so magnetism has to deal with the fact that you have these electrons and they're in these half-filled orbitals, and so they're not paired up, right? So if they're not paired up, then they can be this, when they're all spinning in the same direction, there's a certain amount of charge that goes with it, right? So there's like a positive or a negative with that, right? When they're paired, then you have one spinning up and one spinning down, and so they're cancel out. So paramagnetic means that you are going to be unpaired, or you have an unpaired electron. Diamagnetic means that all of your electrons are paired. So if we look at this molecular orbital for Si with P, would you say that bond is paramagnetic or diamagnetic?
Para?
Para, because it's got one unpaired electron there.
In the 3p?
In the pi 3p bonding orbital. Right, so it's a mouthful to say, but it's your pi orbitals, it's in the 3p energy level, and it's going to be your bonding.
Are you looking at the top one?
I'm looking at this top one, right? I'm looking at this one.
That one.
Because I'm not, once we mix them, we're now talking about the molecular orbitals. We're not worried about their atomic orbitals. That was what was happening before the bond was made. Once the bond's made, then we're only looking at the stuff in the middle.
Professor Lau, just to clarify, for bond orders, if it's 2.5, do you round up or down?
You don't round.
So how do you know if it's triple or double?
So this one would be a blend between a double bond and a triple bond, right? So in the same way that you could have resonance and you could have a single bond and a double bond, and so your bond order will be 1.5, you can do the same thing with your bond order here, right? And so it's telling us that we have a mixture, that you don't have a double bond and you don't have a triple bond, you have something in between.
So one thing I kind of thought that was strange between these two examples, I guess this one with the silicon and the phosphorus, it kind of makes sense, just because you have that sigma bond first and then the pi bonds, right? Which I think kind of goes with you know, like what we've been learning, like the sigma bond gets filled first. That's the one between the atoms. I know. So for like the oxygen, I think that one had the pi bonds first.
And so that flip happens based on their nucleus and their electronegativities and where that spread is. So there's a reason why, and certain ones will follow one characteristic and certain ones will follow another one. I'm not having you guys worry about it. I think that it's not, people struggle already enough with just getting the MO diagrams. I don't think that you have to worry on top of that about why there's a flip. But basically it has to deal with your nucleus and their electronegativities. And so basically what happens is your pi's, from where they are overlapping, end up being a lower energy state than your sigma does.
So the pi's actually end up being filled first.
So the pi's end up getting filled first for these molecular orbitals. Yeah.
That's the question that I had from before. That's why I brought that up. But since we don't have to deal with it on the exam, I guess we don't have to.
Yeah. And so they do talk about it in your book. So there is that explanation, but it's basically this concept that they're interacting with each other. And so your pi bonds versus your sigma bonds, and the energies that they have associated with them, it's different based on your electronegativities, the strength of your nucleus, and basically your effective nuclear charge. So all three of those things kind of play a role. And so you can see that these ones are kind of like electron weak, and these ones are electron heavy, right? So they have a large density of electrons, whereas these ones don't have as much. And so that plays a factor in why you do one versus the other.
So for the kind of problems that we're going to be doing, though, it's like you could even if it was like weird like oxygen, I would think you would still be able to tell like which one is a pi, right? Because the difference between the like having one box or two boxes, and then
exactly.
the anti-bondings are always on the top.
So anti-bondings will always be on top. Pi's will always be two boxes. Sigma will always be one box, right? So you'll always be able to tell.
Yeah, this is actually a lot easier than like I thought it was, I guess, at first. I think maybe because I don't think there was examples of this in like homework 10, so I might have been a bit confused at first, but like seeing like it gone through, it's actually pretty simple.
So the way that we're doing it is a pretty straightforward. Molecular orbital theory itself is a very complex topic. And so the way that I view it is we are giving you a primer on it. So that way, when you take your upper div class and they go more in depth with it, that you are familiar with it. But you won't come back into MO theory for a while, right? You get much more into it at like the graduate level, was where we really started to solve and create big MO diagrams. So I just don't think that it's worth it for you guys to like get really deep into this because it doesn't show up that much.
So it's very like introductory what we're doing.
Yes, so we're doing like the very beginning parts of it, just so that way you guys can get used to this concept that your electrons, once you start forming these molecules, they start to get delocalized over the entire thing.
And I'm sure this will go more in depth into like Chem 2, right?
So Chem 121 talks about it a little bit, but not that much more. To be honest, 121 gets way more into like your equilibrium side of things, your kinetics, why reactions happen. And like for our class, we treat all of our reactions as going from reactants all the way to the products. They start to look at, well, when you do a chemical reaction, if it only goes part of the way, right? What different factors you have there, right? So even Chem 121 doesn't do huge amounts of MO diagrams. It really doesn't come back until later on when you guys get into like inorganic chemistry, a little bit with organic chemistry because they talk about delocalization, but it's just not a huge topic.
Why can we? So the bond order is 2.5, and why do we know a bond occurs because of that?
So if you are a bond order of 0, right? A 0 would mean that you have just as many electrons in your antibonding as you have in your bonding, right? So the more electrons you have in your bonding, the more energy benefit there is, right? Because all of your bonding orbitals are lower energy than where they started from. So the more bonding electrons you have, then the higher this bond order is, because you have more electrons kind of getting an energy benefit, right? The more anti-bonding electrons you have, then the lower your bond order becomes. And so you're not getting as big of a benefit. So if you are at 0, then there's really no benefit for you to be together than there is for you guys to be apart. Right? So that's why we say that no bond occurs if your bond order is 0, because there's just as many anti-bonding electrons as there are bonding electrons.
Okay, so and then also, would we ever get 2 elements that are not in the same period, or?
Yeah. So if you didn't have this as phosphorus, let's say that this one was nitrogen, then what's going to change is this is going to become a 2s, this would become a 2p, and then these ones, instead of being your 3s, these would just be s orbitals, and then these ones would be p orbitals.
Okay, so if they're in different periods, we don't have to worry about the...
You're not looking at your energy level, because really what's happening is you're looking at the overlap between their shapes.
Okay, so we'll just do S and P. We won't do the 3 part.
Yeah.
Okay.
But to be honest, for what we're doing, you always get ones in the same period.
Okay, and then last question, for the molecular orbitals that are not, that don't have any electrons on it, do we still need to label those, right?
Label all of them.
Okay.
Yeah. So if there's a line there, just label them all. I don't think it hurts to not label them. And it's just a way for me to know that you know that those top ones are anti-bonding.
Thanks.
All right. Any final questions? Otherwise, I got to head off to a meeting.
I think one thing is I looked for the chapter 11 kind of section on Canvas, and I think it might not have the like the usual chapter expectations. So I was wondering if we could just like maybe add those in for chapter 11.
Oh, I'll double check that. Thank you. You're right. Maybe I didn't pull them over. Okay, I can get that fixed. I'll do that. Thank you for letting me know. Any other ones?
I did have a question, but if I could talk to you like after class or after everybody.
Okay. So hang out, and then we'll do that in just a second. Perfect.